Hi, folks. We're going to talk just briefly about allosteric enzyme regulation. So the two learning objectives that these slides are really going to touch on are comparing contrasting Michaelis-Menten enzymes and allosteric enzymes, and also explain our diagram how allosteric regulation affects the rate of enzymatic reactions. So hopefully you remember Michaelis-Menten kinetics. We've spent some time on it and done some practice problems on it. This is the Michaelis-Menten equation. And this is a classic Michaelis-Menten plot where we have substrate concentration on the X, reaction velocity on the Y, with our Vmax up here at the top. And we can see this plot of reaction velocities as substrate concentration changes. We're also showing Km, that is the substrate concentration at the point where V0 is equal to Vmax over 2, half of Vmax. So this is the type of enzyme we've talked about thus far. But a lot of biochemical enzymes are allosterically regulated, and they don't follow Michaelis-Menten principles. So there are lots of enzymes that are of the class Michaelis-Menten enzymes, and they tend to be regulated by the concentration of substrate inside the cell. If you'll recall what we spoke about in class on Monday, these guys tend to be regulated by the concentration of substrate in the cell because that directly affects how fast the reaction is moving. Okay. Allosterically regulated enzymes, on the other hand, do still bind to their substrate, but they can also respond to environmental signals that can help regulate their activity. Allosteric compounds are non-substrate compounds that can bind to these enzymes and help regulate the speed of the reaction. Allosterically regulated enzymes, because they can respond to environmental signals, they are often catalyzing the committed step in a biochemical pathway. That is the step beyond which there's no return. We're moving forward with this pathway. Allosterically regulated enzymes tend to have tertiary structure, or quaternary structure, so that we're talking about multiple subunits of a given protein or proteins working together to do the enzymatic reaction. So they have multiple active sites. And because of all of this, they tend to have more complicated kinetics than just the Michaelis-Menten curve. Let's talk about an example of allosteric regulation. So this is a really classic example. We're going from threonine, an amino acid, to isoleucine, another amino acid. But to get from point A to point B, I guess point threonine to point isoleucine, we have to go through 4 intermediates. So threonine is converted into intermediate A by enzyme 1. A is then converted to B. B is converted to C. C is converted to D. And finally, with the help of enzyme 5, D is converted to isoleucine. So for each step in this process, we have a separate enzyme that is catalyzing the reaction, taking one thing as a substrate, producing a product, and then this product becomes the substrate for the next enzyme. Okay. In an allosteric inhibition, this final product of the pathway, isoleucine, can go back and bind to the catalytic enzyme, but it's not binding at the active site. You can see it's binding at another site, the allosteric site. Allosteric literally means other, like shape, other place. So we've got isoleucine, in this case, an allosteric inhibitor, binding somewhere else on the enzyme and changing the enzyme's ability to bind threonine. Okay, so enzyme 1 is inhibited by the binding of isoleucine. And the consequence of that is that we turn down the volume on this pathway. We've got so much isoleucine around that it's negatively feeding back. It's inhibiting enzyme 1 because we've got plenty of isoleucine. There's no reason to keep making isoleucine. Over time, though, the cell is going to use up the isoleucine. So this now inhibitory signal will be depleted. Enzyme 1 will be free now to continue to produce isoleucine, or really enzyme 1 will be free to produce product A, and then product A can be converted until ultimately we make up the level of isoleucine that the cell needs again. So this is sort of a seesaw or a teeter-totter of making more until it inhibits, and then making some more until it inhibits, and then making some more. Yep. And you can see, like we described earlier, the allosteric inhibition is happening at this first step in the pathway. It's happening at the first committed step. Now, threonine could go off to become other things inside the cell, but the activity of enzyme 1 is what commits us to this isoleucine pathway. And so this is what is regulated by the final product, isoleucine. Your textbook gives another diagram, but it's showing exactly the same thing. So for example, we could have A that gets converted to B with the help of enzyme 1. B is converted to C, to D, to E, to F. And at the same time, we've got some compound G that's converted to H with the help of enzyme 10, and H is converted to I. Okay, let's think about, I would like to just focus on this blue pathway at the top. A becomes B, becomes C, becomes D, becomes E, becomes F. You can see that F can feed back and negatively affect the activity of the first enzyme in the pathway. This is just like what we just saw with isoleucine. The final output of the pathway can negatively feed back on that first committed step. Well, let's look down here at the bottom then. We can also see that I comes back and negatively affects enzyme 10. That is the first committed step in this pathway. Okay. Now let's combine blue and orange together. So thing F and thing I come together with enzyme 21. Enzyme 21 converts the two substrate molecules into a single product J. And then enzyme 22 converts J into K. And K is our final output of this pathway. These arrows are showing us that K can feed back. If we've got lots of K around, if this enzyme pathway has done its job and we've got so much K around, K is going to feed back and inhibit the activity of this pathway and also of this little orange pathway down here. Because I don't need more F and I if I've got plenty of K, right? K is the terminal output of this pathway. Okay, you can also see that if we have a buildup of F, so if we've got a lot of A becoming B, C, D, E, F, lots of F, F can positively activate through allosteric activation, right? It's not that F is binding in the active site of enzyme 10. Instead, F is binding somewhere else on the protein molecule and encouraging it to be more active, right? So if we've got lots of F, hey, you guys, come on, let's make some I so that we can ultimately, build some K. And similarly, if we've got lots of I, it can feed back to activate enzyme 1 to say, let's make some more F, you guys. I'm just standing around here being bored. So that's the idea of allosteric regulation. We're responding to the environment of the cell, and it's often the first enzyme in the pathway that's regulated, And we can have multiple like downstream effectors that can allosterically bind, non-competitively inhibit the enzyme. Yeah, it is important to note that when we're saying that K can come back and allosterically inhibit or allosterically negatively regulate, allosteric regulators are non-competitive inhibitors or non-competitive activators. They're not binding to the active site. They're not competing for space in the active site. Instead, they're binding somewhere else. They're binding allosterically. So they're non-competitive inhibitors. Okay. So this illustration comes from your textbook, or it's kind of modified from your textbook. And remember we said earlier, allosteric enzymes often have quaternary structure. That is, often we have multiple subunits of the enzyme coming together. And those subunits together are really what's the active version of the protein. So you can see here in the squares, squares represent the inactive state of the enzyme. Okay. And then here in circles, we've got the active state of the enzyme. And then when it's got pink, you can see it's bound to the substrate. Okay. So on the left here, we've got very low substrate concentrations. And what that means is most of the enzymes are in the inactive state. There are some that are in the yes active state. And some of those in the yes active state have even bound a substrate molecule. However, if we're in a higher substrate concentration environment, you can see that anybody who is bound to the substrate now has converted into this shape of an active enzyme. That is, you can't remain in the inactive state if you're binding the substrate. You can be in the yes active state without binding the substrate, but you can't be in the you can't be in the inactive formation if you've bound the substrate. Because each of these subunits of the quaternary structure, each of them have their own active site. And so that means 1 or 2 or 3 or all of the enzymes, all of the subunits making up the larger enzyme can each be binding their own copy of the substrate. Okay. Terrific. What comes next? So the next thing we want to look at is comparing the Michaelis-Menten curve. You can see here with Michaelis-Menten, initial reaction velocity tends to shoot up as we just marginally increase the substrate concentration, right? Reaction velocity goes up very fast as we increase the substrate concentration until we've sort of used up most of the enzyme active sites. And you can see a similar thing here, right? The allosteric enzyme in pink, we do at some point, we have at some point used up all of the enzyme active sites, and the reaction velocity doesn't increase very much more, even as we add more substrate. But the thing that makes the allosteric enzyme activation curve different is that it's this sigmoidal or S-shaped curve. And what that means is that we've got a little bit of a lag here. So we're increasing substrate, we're increasing, and it's only after a while we're actually increasing the rate of enzyme activity, okay? And that's due to the fact that we have to shift first from an inactive state to an active state before you can actually bind any substrate, right? So increasing amounts of substrate are going to tend to push these inactive forms into an active form, but there is a little bit of a delay, and at a low substrate concentration, there's not going to be much like driving factor to convert these enzymes to the active form. Once they're converted, though, now increasing substrate concentration is going to allow reaction velocity to jump up, and of course, we'll eventually reach or near Vmax. Okay, so it's due to the fact that allosteric enzymes have this quaternary structure that can be both in an inactive and then converted to an active state that we see this lag in activation at low substrate concentrations. Okay. The next thing we're going to talk about is this curve, also from your textbook. So on the y-axis here, we've got enzyme activity, right? This is rate of reaction, rate of N-carbamoyl aspartate formation. And on the x-axis, we've got substrate concentration, 10, 20, 30 millimolar, starting at 0 here. You can see that classic sigmoidal curve. And in black here, you can see the baseline enzyme activity that produces carbamoyl aspartate. And then we've got the reaction done with one of two different allosteric regulators. We've got 2 millimolar ATP, and that's the blue curve here. 0.4 millimolar CTP. That's the pink curve here. I want you to think for a minute about which one of these is going to be the allosteric activator and which one will be the allosteric inhibitor. So you can stop the video for a second, think about that, and we'll talk about it in a moment. Okay, so the enzyme that we're looking at here is aspartate transcarbamoylase, but it doesn't really matter what the name of the protein is. Instead, let's talk about what we're seeing in these curves here. So first of all, in the black curve, the unchallenged reaction, the unregulated reaction, we see a slow increase. Then at some point, we really start to ramp up the reaction rate, and then slowing up here as we get closer to Vmax. And remember that this lag here is due to the time it takes to get from the inactive state to the active state. And I would call this inactive state the R form, the relaxed form. And we'll talk more about this as we get into glucose metabolism. The 2 millimolar ATP, well, it's not the substrate that we're worried about here. We're talking about this allosteric regulator. It looks like maybe the sigmoidal curve is going up a little faster, and then we're raising the rate of product formation just a little bit more quickly. But of course, we have the same Vmax because it's the same enzyme. So that jump here from being inactive to being active more quickly, right? Sort of the sharper S curve is suggesting that this ATP is helping increase the rate of reaction. Really what this is doing to the allosteric enzyme is stabilizing this active structure of the enzyme. So ATP binding to the allosteric site, not the active site, is going to stabilize this active form of the enzyme. And if ATP has stabilized this active form of the enzyme, then there's less reason, like less need to be converting from inactive to yes active, because we're already active. ATP is bound and convinced us that active is the best shape to be in. Okay, so ATP can activate enzyme activity through allosteric binding, whereas if this one's activating, CTP must be inhibiting. And you can see here that this S curve lag is much longer with the CTP. And that's because CTP is going to be stabilizing this inactive state of the enzyme. So it takes a lot more substrate, before we have very much enzyme converting over here to the active state, where we can start to see a real ramp up in reaction rate. Okay, so activators can help stabilize the active state. Inhibitors can help stabilize the inactive state. And it's going to be the balance of those two that makes up this, the rate of reaction curve, that sigmoidal rate of reaction curve for an allosteric enzyme. All right, so I think that's all I wanted to talk about to introduce allosteric enzymes. We'll definitely be talking about more of these as the weeks go on, and especially as we get into glucose metabolism. We'll see a lot of these guys. All right, thank you very much.